Elizabeth Gasparim from Antofagasta in Chile, and she's going to be speaking about deformations of local surfaces and Calabi-Yau threefolds.
Thank you. Okay, good morning. Let me first thank the organizers for inviting me. It's a pleasure to be here. Okay, so most of the time, like half of the time, I want to tell you why we got to study this, the formations of these local things. So first I want to tell you the sad story of how we try to compactify, and then you'll see. All right, so this is how it went. We were looking for Landau-Ginzburg models, A-side stuff, symplectic things, and then I'll show you like lots of trouble we have with compactification. So Landau-Ginzburg model here is a symplectic manifold with a complex function. People know a lot about this. And I have to remind you a little bit of things that I said last time for a motivation. So our examples were the case where our symplectic manifold was a joint orbit of some simple Lie algebra. So this is part of that is joint work with Lino, who's here, and San Martin. And then the second part with Brian and Eduardo Balico. All right, so the definition, you don't need to see all of that, but just to clarify what it was for people who don't know it. It will be a fibration where the singularities are of Morse type, the simplest type possible, they are quadratic. You don't need to remember any of the definition, I'm just putting it in case someone wanted to see the details. But at this point, which was about 2 years ago, we were looking for examples of symplectic left-shaped fibrations in dimensions higher than 4. So we wanted, first of all, complex threefolds or higher. So we're looking for that. The symplectic case is when the total space and the regular fibers are symplectic submanifolds. And I will immediately pass to the examples we found. Then if anybody wants to see details of the definition, I can go back to it. But for now, trust me, we found all the conditions. We were, of course, looking to find stuff which belongs to this side, and this, everybody here is really familiar. And as we know, a lot more is known on the algebraic side, so we're trying to contribute to symplectic side, right? So, just recalling some definitions. So the usual thing, Cartan-Killing form on the Lie algebra, a Cartan subalgebra, which here I'm going to just take to be diagonal matrices in SLN. And we pick two elements in the Cartan subalgebra. One of them is going to be regular. That means we will have two diagonal matrices, one generic, and the other one with distinct eigenvalues. Okay, so this is set up. Our space was a favorite space where at the adjoint orbits, I'll just recall the definition. So, and now, so the result we have is that, so now we picked any element of the semisimple Lie algebra, consider its orbit, here it is, and then we show that the adjoint orbit of any of such elements has the structure of a symplectic left-shaped fibration. We are defining the function. So this is our potential. So the potential is defined in a very simple way. Right? So for every element h, we define what's called the height with respect to h. So this is our function, very, very simply defined, which goes from the adjoint orbit of h naught to c, and happily enough, it satisfies all the conditions. It's of course, we are very happy to find that it satisfies everything. The hardest part was to actually put the correct symplectic form. Because if one puts the KKS form, like bring it from the co-adjoint orbits, it doesn't work at all. It's actually quite simple to show that if you put the KKS form, then the symplectic submanifolds for here, for the regular values, then the fibers, the regular fibers of this, do not turn out to be symplectic submanifolds. It just degenerates. So it doesn't work. So the hardest part was to choose the correct symplectic form. And then, I'll show you in a second. So I'm just recalling what are the conditions that happen. That means that we now have this non-degenerate singularities, actually of quadratic type. We will have that the regular values will give us regular fibers that are diffeomorphic, as it needs to be, and a good choice of symplectic form, which gives us that the regular fibers are symplectic submanifolds, and all the conditions that we need. The choice is this, which for me was actually much easier. We take the Hermitian form from the Lie algebra and simply pick the imaginary part. And this is, for me, it was much easier, a choice of symplectic form, because you see, now every time we take something of half dimension, which is real, it's automatic Lagrangian. So if we look for, looking for Lagrangian submanifolds, Lagrangian timbals, everything real works. So in fact, we have now found a huge amount of real Lagrangian timbals. But I won't talk about this. I want to talk about a different thing, which is work of my 3 PhD students. So now I'm going to be showing the stuff that they did related to that. Okay. The only thing I want to comment is, because it's the part I like best, is what are the singularities of this fibration. So the singular points are the vial images of the original guy we chose. So it's very clear to pick in the fibration who they are. Okay, so I'll describe just a little bit because one wants, of course, to know what are the regular fibers, and then we want to find Hodge numbers of them and everything, right? So here's the identification of the regular. We called it level because it turned out that the word fiber was used in many senses. So we called it a regular level. And this is identified as an affine subbundle of some cotangent bundle with a flag, as a diffeomorphism type, not as a symplectic type. And so because we have the precise identification of this, we know the Betti numbers. So our Betti number is k minus 1, where k is the number of singularities. Now remember, the singularities are the images of the vial images of the original guy. So that means we can have, first of all, this symplectic left shift fibration of as big a dimension as you like, and with as many singularities as you like. So a lot of, so potentially huge amounts of vanishing cycles. So we're happy about that there are many singularities and so on. So this is the regular fiber, the critical fiber, and so on. Yeah, so we get middle Betti numbers, which are very big. And of course, we want to find them. All right, so we want to calculate more details about this. Actually, I hadn't realized before, if you give your algebraic variety with whatever polynomials, and then you want to compute, let's say, the middle homology, given the equations that describe it, it's terrible. You can't, for example, how can you try to do like the cell decomposition of, for example, in the case of SL3, the orbit, let's say, of the element 2 minus 1 minus 1. This gets described by 9 polynomials inside of an 8-dimensional space. It's not a complete intersection. You can't remove the polynomials. It becomes terrible. But then we find out happily that you just compactify, you put on Macaulay, you calculate the command HHPQ, and it gives you Hodge numbers. So we're happy. So let's try to do that, right? Example. So easiest example possible. We take these guys, both of them the simplest thing, and we're going to look at the adjoint orbit of SL2. And we're all very optimistic. We're told, oh, this is done by Lie theory, so everything is going to be easy and work out smoothly. So let's go. We have 2 critical points, this and minus that, as we expect. So this gives us a complex surface. As the only case where the adjoint orbit is actually described as a hypersurface inside the Lie algebra. The other cases, it will be higher codimension. And, okay, so we compute the Fukaya-Saido category. It's a lot of work, but we work and then we find. This is pretty much well known already in various different setups. But just a remark, we're not working with cotangent bundle of P1 here. It's actually a complex deformation of it, and it's affine. It's clearly affine, right? These guys are affine because these adjoint orbits are defined by polynomial equations inside the Lie algebra. All right. Then we try to look for the mirror, and then we have this very sad story, or happy, whichever you like, no? That this, which is the very first case, the simplest possible, has no projective mirror, by which we mean there is no projective algebraic variety whatsoever, such that the derived category of coherent sheaves is equivalent to that Fukaya category we just gave here. It's simply not possible. So, okay, so everybody tells us, oh, this is terrible, it's because you didn't compactify the model. Okay, so we compactified. And well, I'm glad people laugh about it. It wasn't, anyway. All right, so we thought, all right, but maybe next time, right? Let's go to the next example. Maybe it's just bad luck because this guy is too easy, so let's take this. This is what we want. And we, again, we choose age and out like this, and we're going to compute again, right? So this one now has 3 critical values. And do we compute? So we compactify. Now this is how to compactify. Come on, we have an affine variety. In this case, I can define it very easily and write down the polynomials and homogenize, so no problem, right? Oh, this is a reminder. This was for a different audience, but you don't need it, but because I have pretty colors, I'll show it anyway. You know what it is. Example you also know, and mirror you also know. I can pass quickly, but this example, let me show it first because it was happier. We first computed this because it was easier, and we got this for the total space. So my student did that in his master thesis. Then one compactifies, and then he got the following thing for the regular fiber. So he brought that to me, and said, oh, look, I got this. We verified, and we got this. And I said, congratulations. You've now constructed a counterexample to the fundamental theorem of Picard-Lefschetz theory. We have a fibration with singular fibers. It has all zeros, right? That's catastrophic. Okay, so that's not so bad. I mean, here is the fundamental theorem. We all know for every singularity that exists a vanishing cycle, etc., etc. So what happened in his case is that when you compactify, you have stuff which is not of Morse type. And so, okay, fine, so we're happy. Let's go for my example, which I claim this must be much easier because this is the regular guy. Right? So let's do this one. Okay, so I can write the orbit of this inside of SL3 very easily. I can say 2 polynomials, this is easy. I can say eigenvalue 1, eigenvalue 0. This will give me the stuff, right? So, you see, I'm going to write inside of SL3 this affine variety as these 2 polynomials. So if a matrix belongs to the orbit, it has to have those eigenvalues. So in this case, it's determined by eigenvalue 0, eigenvalue 1, 2 polynomials. So I'm going to compute with this idea. So, and okay, here's the potential. So we're computing directly. We want to compute directly the Hodge diamond of a regular fiber. And the same student, of course, tells me, no, Elizabeth, this is nonsense. This is cubic, it's too difficult, I'll do this. Obviously, it's the same. I said, fine, you do this, you're going to find my answer anyway, right? Here's what happens. So this is absolutely terrible. And they're correct. You see what happens. So this is my diamond, this is his diamond. So I'll go back. This is my ideal, and this is his ideal. Obviously the same. Now we take this guy, put him in Macaulay, homogenize, I get this, he gets that. And they're both correct. And it's not our fault. It's the fault that if you homogenize, you take a basis, you homogenize the polynomials, you generate the ideal, it's not unique. So now we're even in bigger hell, because I feel that I can get like anything here. These ones we couldn't get because we ran out of memory. But then again, like, oh my God, what are we going to do? We go to all these conferences and then we hear, this doesn't depend on compactification, that doesn't depend on compactification. Okay, so we're lost. Well, anyway, and we can't compute one. This is like how fast it goes, 45 gigabytes in 3 days. It's too big. Oh, actually, this was computed in India. We can't compute this. I said to my Indian colleagues, I was going to say that I was doing like Bill Gates outsourcing the work to India. They told me I can't say that, it looks terrible. But it was true. but it was true, they did it. All right, so we still could calculate some mirrors, right? Easy stuff. But anyway, what to do? So then I asked Kenji, I said, Kenji, I'm desperate. If we look at this, what to do? What compactification do I choose? So Kenji told me, no, it's easy. You take your variety, you deform it, like, calculate the deformations. When you understand the deformations, you're going to understand what compactifications you should use. And he was right, you see, I show you, it's really going to help. So of course we go for toy models, like let's do the first one. Since the first guy that we have is the surface, which is, it's actually the deformation. There's a unique deformation of the cotangent bundle of P1, which is an affine thing. So that would be total space of -2, so let's do what we can, right? So we do all the surfaces which kind of look like that. We'll look for deformations, try to see what to do. And of course, let's do Calabi-Yau threefolds so people will listen to us when we give talks, because otherwise, I mean, people are all going to sleep. All right, so let's go see what happens with the deformation. So we have to deform these guys. Okay. Let me first say, I'm going to talk about the threefolds first. And this will be the work of my PhD student, Francisco. And there are essentially three different cases to consider, because these guys actually happily also turn out to come from problems in mathematical physics that we really want. We're discussing with people like in gravity, cosmology, etc. And they want to understand all these cases of collapsing star, all these beautiful things that the cosmology people do, right? So you have a sphere, you want to contract it. And then on the case where you actually want to contract the sphere, these are on a threefold. These are the three cases. These things then enter into some theories which are called Kodaira-Spencer gravity, which I find sounds very sexy if you just say, oh, I'm going to do that. So we go to look at these cases first of all. All right, so now we want to do deformations. So now I go and discuss with sensational collaborator Baliko. Look, if you look him up in Matsanat, you understand why I say he's sensational. Anyway, he's sensational. And so I go and say, look, Eduardo, we're going to deform this. And, okay, so first trouble. So now he's going to tell me, I'm going to let's imitate Kodaira-Spencer theory. And you calculate cohomology with the coefficients in the tangent bundle. And we want to describe deformations like that, right? So this example is to show the following thing. If I take C, just complex plane. And of course I calculate cohomology, obviously I'm going to get 0. However, this doesn't imply there are no deformations. Here are the deformations. So let's consider this. So we take P1, cross a disk, and with a 0, right, in the disk. Now I'm going to take two sections which are intersecting at a point. So my two sections, I mean, that's what he gave us. One you pick an infinity in P1, and here you put x for any x. And the other section you take infinity 0 at 0, otherwise any a and x. So you have two sections like that. And now you look at the fibers of this over the disk. And what happens? So first you are on P1, right? So if you're looking at P1s, you have P1 minus a point in one position, P1 minus 2 points in another position. So this gives me a family where the central fiber now, when I look at it without the infinity, that the central fiber will be C, but all the others are C minus 0. So if I call the problem is the definition of deformation. If I just want a flat map, then I can simply take C and start removing points, or any variety, and start removing points, but I don't want this, guys. I want to honestly define the complex structure. And this one is just changing the variety too much. Okay, so definition. Now, this is arguable, but for example, Tony told me, okay, fine. The referee told us, not fine. But anyway, this is what I'm going to use right now, because we simply don't want to change the topology of the manifold. We don't want to change the diffeomorphism type. We just want to change the complex structure. So this is maybe an ad hoc definition, but it works. At least it's not going to give us that trouble that you're deforming stuff to things which is topologically different. So for us, now, we decided this is our definition of deformation. You take a disk, the central fiber has to be, of course, the guy you started with, and we impose that it's trivial in the C-infinity category, but not on the holomorphic category. Well, not necessarily. You could have the trivial family, so this is our definition. Objections? No, okay. Now I need you to be okay with it, because from now on I'm doing just this, right? Okay, so what happens? So let's see what happens. So, comments. Usually we now, even anyway, going to choose the dimension of this as this. Because you see, if I calculate something and the cohomology is 0, well, I can't really say anything. I don't know. We haven't proved exactly the relation between this cohomology and our definition. If I calculate the cohomology and it's not 0 and gives me directions, I try to integrate. And if I integrate and I get a family, then I got the family. So I can still use Kodaira-Spencer theory as a tool, even though we don't know the full theory of what we're doing yet, but let's try. Right. So in general, well, we don't really know. Actually, I should have said we don't really know what's happening when you have the cohomology 0, but anyway, we know this. So then we take our W1. Remember, W1 was the resolved conifold, right? Total space of -1, -1. So that guy has no deformations. So you calculate H1 coefficients tangent bundle, it's 0. Okay, so that was said. Let's go to the next. Now the next is good, you see. Now we take W2. This is actually cotangent bundle of B1 cross C. It's the case where the singularity actually moves when you contract, right? It moves in a family. So you see, we are very amused. You calculate the cohomology with coefficients on the tangent bundle, and it's infinite dimensional. And now, okay, calculate the cohomology is quick, right? You do it in, I don't know, 10 minutes. But now you have to find out, do you actually have, so does it integrate? Do you actually have complex manifolds in this family so that they are actually deformations of what you start with? And that's a lot of work, but you can play it like this, right? You can do an additional theory, because deforming the manifolds is difficult, but deforming a vector bundle is very easy. So we took the tangent bundle as a tool and deform it as a vector bundle, and now you look at the deformation and ask, is it the tangent bundle of somebody? But that we can do. You integrate some stuff and you then find out what it is. So what Francisco did is he effectively wrote down the family, the infinite dimensional family of the deformations. But then, of course, we go and show it to Balik and say, look, it's great, it's infinite dimensional. And he said, but maybe there are two, right? Maybe, maybe in the end, the different directions, Francisco had shown that any direction of deformation that he obtained was non-trivial. But maybe 2 by 2, they're all equal, and in the end, there are like only 2. So, but then Bruno, well, together with me, then we show that you take any 2 directions, and they actually produce non-isomorphic stuff. So that means this deformation family is honestly infinite dimensional. You can't kill it. And that also means that Kenji was right, because now it tells me which compactification I can use. Nothing, absolutely no compactification. It's simply not possible. Whatever way I compactify, I'm never going to find the entire deformation family. That's simply a problem which gives me an infinite dimensional holomorphic family of different things. So it's fun, we like it. We're very happy with that. We started looking for geometric reasons. Why is this happening? So let's see, right? How non-algebraic is the situation? So then we construct holomorphic bundles that are not algebraic. Of course, you can write exponential, right? But then you have to, like for 2 weeks, trouble and think about it and dream of this bundle until you can actually prove that you cannot convert it, change coordinates or whatever, to make it algebraic. But you actually can't. So this has properly holomorphic bundles. And if you actually write down an extension class, let's say, you can deform individual monomials. And when you deform just one coefficient, the thing then turns out not holomorphically equivalent to the original one. So, all right. Okay, so we're happy, right? We did something. on the threefolds, so Severin, my German student, tells me, but why you did the threefolds? Let's do the surfaces, right? I mean, you need the surfaces. I'm like, no, okay, let's do the surfaces. That's gonna be easier. All right, so we go to surfaces. So then Severin and Bruno like the surfaces. We calculate the deformations. I'm happy. So now it's a different application, you see. The mathematical physics application of the threefold case that we have in mind is this thing called Kodaira-Spencer gravity. It's something different. Here, the actual application is instant-on gauge theory and so on. Now, it's much better known stuff because we start on the surface that we have. We know how to calculate all instantons. There is a version of Kobayashi-Hitching correspondence. We calculate the moduli spaces of instantons. They're huge. We have lots of stuff. We calculate the deformations, and then it turns out all deformations are affine. That means the bundles are trivial, and that means there are no instantons. The instantons all died. And now we're even more depressed. Now all the physics has disappeared, right? This is absolutely terrible. I mean, it can't be. You can't be. You're in the space. You have all this huge amount of instanton moduli. You move it a little bit, it's all gone. It's just completely pathetic. So we have no other option than to do non-commutative deformations because the instantons have to go somewhere. So we go non-commutative. All right, so we start to compute. Right? Now it's a lot of algebra. So first we start with Poisson structures, of course, we calculate it. It's easy to calculate. And these surfaces are very easy. They have this, what we call canonical coordinates, which is just, I mean, let me explain this. People always complain, they say that this is physics. But it's easy, right? Even if it was physics. I mean, this is my vector bundle for P1. The first coordinate is the P1. See? Z goes to Z minus 1, that's my P1. The second coordinate is giving me the O minus K line bundle. So it's easy, we can write it down. And now we want to look for a star product on it, right? We want deformation quantization of the original guy. So we recall Koncevich's product, but you see, the original guy is not affine. The deformations are affine, but the original guy is not affine. So I can't just go there, put Koncevich's product for affine manifolds and be happy with it. So we work with it. Anyway, this is just recalling the star product, which is very well known. And then Severin has, I love this slide, it's so pretty. Severin has this beautiful way to draw stuff. And he actually uses this to calculate. So here are our coefficients, and we start calculating products and see what happens. So this is recall of the Koncevic star product, which we can try to use like in one chart. And then we say, no, but here, let's say, what if we take Koncevic product and try to extend it? Maybe it extends, right? Maybe we're lucky. I mean, we never know. So let's look at this case first, which is the holomorphic symplectic case, the easiest one. And so Francisco and Severin calculate, put the Koncevic product here, which in this case is the Moyal product, and it simply doesn't work. It's impossible. There is no way to extend. You can't do it. And there are two proofs, one which was totally algebraic. I didn't put the rest. It was long. And this one, which is quite simple, actually. You simply take two global functions, start it, and get stuff. This coefficient is not a global function, so you're done. So simply, there's no way. Forget this one. Well, let's try the other one. I mean, why not? So we try the other, and then example. So I take the Poisson structure, which is this one. And then we actually follow the graphs. Right? Every time you start to calculate coefficients of H bar, what happens is the powers of Z and U are lowering by the same amount. So if we are on this Poisson structure, let's say I'm on B1. So I lower a Z, I lower a U, but then I multiply back, and things work happily. So, okay, you have to write the stuff that's terrible to read, but in the end it works. So if I just put the Koncevic product in the U chart and I continue by hand, like on this one, it works out just fine. So now we want to propose a definition. I will give it here. I don't know if it sounds either beautiful or terrible. I have to ask Maxime later if he allows me to put this as the definition. But we would like to say the following thing. Consider that you have a manifold, and of course you take an affine chart, you put Koncevic product in it, and suppose it extends. Then I would like to do the following definition. So let's see. Let's see if Maxime allows me to call it this way, but yeah, that's the same I find it's fun. Anyway, I'll ask him. But for now, provisory definition, and this is the last thing I want to. I can't be serious. It's too fun. But but anyway, it's a great name, right? We also tried Maximable, but that sounds even worse, right? So anyway, but look what happens actually. It always works. Well, it's more delicate than that. We had to divide the Poisson structures into types according to the generacy type. So it got divided into 3 types. And I'm just giving you the conclusion for type 3. But what happens is for these guys, all the Poisson structures are of type 3. That depends on the genealogy, locus, etc. But it's delicate, so I don't want to say no. But the point is that it simply works. And so what happens then when you go to the interpretation, the instant interpretation? So you take the original guy, you take a deformation, and let's say I evaluated a small value of h bar. And what it actually gives me is a curve inside the moduli space of the original moduli space of instantons. So these things are actually moving around. So we found the instantons again, so we were extremely happy about it. So I quit. Thank you for listening.
Any questions?
Yes?
For holomorphic vector bundles on, say, quasi-projective but non-complete varieties,
Yes?
there's a measure of the level of transcendence of the holomorphic vector bundle, how far off it is from being algebraic.
Oh, I see.
And does that enter into this?
I
So
don't-
roughly speaking, you take sections of the bundle that's on a non-compact complex manifold that has a boundary at infinity.
Yes.
Look at the area where the sections become dependent. Those are the term, the Schubert cycles.
Right.
And see how the area grows. If the area is bounded, it's algebraic. So if it grows like a polynomial, it's finite order, etc. Does that sort of thing?
I don't know, we haven't looked at it yet, but I know I must check such type of things. In principle, the idea is I guess we're going to have to divide up into different directions according to certain geometric behavior, so that we can actually study the family more geometrically. But we just freshly did it, so I don't know yet. I'll think about it. Thank you.
Any other questions?
I have a question. Do we want to place a bet on who is going to gossip to Maxime first? Thank you for listening.
Well, thank you so much.
Thank you.